Morning, everyone. Welcome everyone for day 9 session, four-note session, lecture 22. Title of today's presentation is Mechanism for Ammonia Decomposition. So the learning objectives to explain the basic principles of ammonia decomposition and its significance in hydrogen production, to understand the reaction mechanism involved in breaking ammonia into hydrogen and nitrogen, to identify key catalysts and factors that affect ammonia decomposition efficiency, to compare different decomposition methods and their suitability for industrial applications. So at the end of the presentation, participant can able to have some idea about what is ammonia decomposition, thermodynamics and kinetics of ammonia decomposition, catalytic mechanisms, non-catalytic and plasma-resistant decomposition, industrial application and process optimization, futures perspective and emerging research. So decomposition is nothing but a breaking of the molecule, nothing but an endothermic process. So you are going to break the ammonia into nitrogen and hydrogen. So you may come across for different lectures from D1 to D8 how to produce the ammonia from the different sources, from other portion or from the electrolysis. Then whenever there is a necessity for hydrogen, either for internal combustion engine or the fuel cell, right? You can employ the decomposition method of ammonia to bring the hydrogen. Even you can generate the hydrogen on board. So that is the advantage of carrying the ammonia instead of carrying the hydrogen, particularly for automobile system. So chemical decomposition or chemical breakdown is the process or effect of simplifying a single chemical entity, normal molecule, or reaction intermediate into two or more fragments. So need not be hydrogen along with nitrogen and some in between there are intermediate reactions are happening to convert ammonia into hydrogen. The intermediate species are yesterday we have seen around 36 intermediate reactions are happening in between. To form nitrogen to ammonia. Similarly, the intermediate species are happening in between to form hydrogen from ammonia. Ammonia decomposition is a process where ammonia breaks down into constituent element nitrogen and hydrogen through the application of heat and by using a catalyst. So nothing but an endothermic process. So need to provide the heat. Heat addition may be either from thermal mode or microwave mode or plasma mode, or radio frequency mode, any kind of mode, but you need a required temperature to break down the ammonia into nitrogen and nitrogen. This reaction is endothermic, meaning it requires energy input. So here, as you is an endothermic process, so you need to maintain the temperature, but you need to find out the energy input, minimum energy input in such a way that you are going to, obtain the required temperature. So Professor John Hu also mentioned that microwave catalysis is going to consume the minimum energy to get the desired output. Same way to attain the reaction temperature of to break down ammonia maybe 600 to 700 degree temperature you need very near to 700 degree. So in order to attain the temperature, you can go for microwave, radio frequency, plasma, and plasma is highly intensive, but microwave and radio frequency may be the technique you can adopt for rising the temperature of the reactor. Ammonia is emerging as a promising hydrogen carrier due to the following advantages. Ammonia contains 17.6% hydrogen by weight. So efficient storage. So compared with storing hydrogen in metal hydrate, solid state of storage, you can store in the form of in the form of gaseous state or in the form of liquid state. But in ammonia, about 17.6% hydrogen. So easy way to transport. Because transportation already the concept was emerged in all over the world, transporting ammonia through road or through the rail or through the ship. So there is no need of going for even transporting through by mail. So there is no need of any kind of new transport medium necessary. So it's already proven technology for carrying the ammonia. So you can easily adopt that technology for using hydrogen for different power generation systems. For clean hydrogen production, decomposition yields only hydrogen with zero carbon emissions. But they are claiming that the product is going to be nitrogen and hydrogen. But what is the mode of energy input you are going to provide to break the ammonia into nitrogen and hydrogen? If it is you are taking the energy from the grid, then it's don't claim that it's with the zero carbon emissions. So even the energy input you are going to provide into the reactor to break hydrogen into nitrogen through green route, then we can claim that with zero carbon emissions. Benefits of ammonia decomposition enables a global hydrogen economy, facilitate the transport and storage of hydrogen, supports renewable energy integration. So need to bring the solar or wind or hydroelectric or the geothermal or wave energy in the form of in the renewable form. Then we can claim that there is a possibility of zero carbon emissions to dissociate ammonia into hydrogen and nitrogen. Okay. Advances in technology, these are advanced catalysts and reactor designs are making the process. Yesterday I saw a paper, journal paper, related to the decomposition of ammonia. They are using microreactors. So they are using a 3D printed microreactor to break down the ammonia into hydrogen efficient. 99.9% conversion efficiency is happened by using microreactor. I think Gopi also did a microreactor for producing the biodiesel, and he has attained the maximum percentage of yield. Similar way, we can think about the flow channel design or something to minimize the pressure drop and maximum conversion. You can even send the catalyst along with the ammonia, or even catalyst can be coated in the microreactor itself. So that is also possible. So this is the scope of the research, advanced research. Rather than even the membrane technology, also people are using to break down ammonia into nitrogen and hydrogen. So temperature based membrane also there. Pressurized, I can say PSA like pressure based membrane also there, but you can also use the catalytic coating membranes. You can able to convert the ammonia into nitrogen and hydrogen. So ammonia decomposition, thermal mode and catalytic mode. So basically, I can say in the catalytic mode is the absorption and desorption, dissociation, recombination. So absorption, the catalytic you need to support for absorbing the nitrogen. Then whenever the desired can say temperature reaches, then the desorption of nitrogen. So absorption and desorption is applicable for absorbing and desorbing nitrogen. Whereas the dissociation and recombination is the process involved for catalytic decomposition for, I can say, collecting the hydrogen and also combining the hydrogen. Okay. So thermal decomposition, as you know that you need to provide energy because of the you know that for every molecule you need some kind of minimum energy to dissociate the molecule, maybe around 100 to 200 kilojoules per mole. Maybe you may be in need of that to break the ammonia. If you provide that heat, it is going to be dissociated in the form of nitrogen or hydrogen. It is going to be again combined in the form of N2 and decombination means it is in the molecular state, whereas the dissociation in the form of atomic state. So mechanism for ammonia decomposition, the thermal decomposition and catalytic decomposition. The thermal decomposition, ammonia molecules gain energy from heat source leading to bond breaking. So whatever may be the amount of energy, how much the temperature you need in the reactor to break the ammonia into nitrogen, that the source of providing heat you need to decide. Then the dissociation, nitrogen bonds break. Then it's going to be in the form of atomic state, N and I can say hydrogen. Then the nitrogen atom, another nitrogen atom will be combined, it forms N2. Similarly, hydrogen atom and another hydrogen atom combined, it produces hydrogen molecule. The released atoms recombine to form hydrogen molecules. It's called recombination. In the catalytic part, the most common method involves using a catalyst to lower the activation energy. Suppose we are providing around, I can say, 1000 kilojoules of energy to break to attain the particular temperature of 700 to 800 degrees to break the ammonia. Here, by going for catalytic way of decomposition, the temperature, because as we all know that catalytic way of the process going to find out the different pathway. So how best minimum energy you need to utilize to break the molecule is going to be happened by using a catalytic coating. Okay, by using a catalytic decomposition method. Okay, so by going for catalytic method compared to thermal decomposition, the amount of energy, the activation energy for activating the particular process is going to be reduced. By doing so, you are going to provide only lesser energy input compared to the thermal decomposition method. So absorption is a method where the ammonia, the nitrogen present in the ammonia is going to be absorbed. Ammonia molecule absorbed onto the active sites of the catalyst surface. Dissociation, the absorbed ammonia molecule undergoes a series of dehydrogenation steps, releasing hydrogen atoms. Decombination, the released hydrogen atoms recombine to form hydrogen. Desorption, the nitrogen atoms recombine to form nitrogen. So the absorption, ammonia is absorbed. Then during that, because nitrogen needs more energy than hydrogen. So during that particular energy heat is attained, then the desorption is going to release the nitrogen. Where the dissociation and recombination pertains to the breaking of hydrogen from the ammonia, then atoms are recombined to produce the hydrogen molecule. So there are four processes happening in the catalytic decomposition: adsorption of ammonia, dissociation of hydrogen from the ammonia, then recombination of hydrogen from the dissociation process, then resorption of whatever may be, because hydrogen, ammonia is stored, ammonia is absorbed, nitrogen having high can say energy, you need high energy to break the molecule. So whenever the hydrogen is taken out from the absorbed ammonia, the remaining leftover and the absorbed catalyst is only nitrogen. So for desorbing, you need to regenerate the process. So nitrogen from the ammonia is going to be comes out, then nitrogen and hydrogen will be comes out from the catalytic process. So factors affecting ammonia decomposition is temperature. So this is very important. Temperature. So this is based on the temperature and the pressure. Normally, if you compare with the pressure, temperature, pressure doesn't have much role in decomposition of ammonia. But we need to break the ammonia into nitrogen and hydrogen. We are more interested on temperature rather than the pressure. So high temperature accelerates the reaction rate. The lower pressure favors the decomposition. Because when you go for higher pressure, it may be you need some kind of residence time to absorb the ammonia over it. It will be immediately, right? The ammonia will be comes out from the reactor very quickly. Then the conversion rate is not going to be, I can say, what we expect. Catalyst, the choice of catalyst significantly influence the reaction rate and efficiency. So, what the type of catalyst you are going to choose in such a way that whether they are lithium or platinum or the ferrous kind of thing, right? Type of catalyst you can use so that for particular catalyst, which catalyst is going to consume the minimum energy to break the ammonia is the I can say it is the research. So people try with many catalysts, but try to find out some new catalyst if it is possible to ensure that the breaking of ammonia happening at lower temperature, even at 200 degrees centigrade. But if we go for thermal decomposition, the temperature around 700 to 800 degrees. At 200 degrees itself, we are able to break the ammonia into nitrogen. Then the minimum amount of energy you are going to consume for the reactor for the endothermic process is going to be reduced. And also increase the surface area, right? So surface area also, catalytic surface area plays a major role. Instead of putting mm size or micron size, increase to nano size or 10 power, more than 10 power minus 9 or minus 10, minus 11 or minus 12 for the particular area. Then the maximum absorption of the ammonia happens during the catalytic process. Then the conversion efficiency of ammonia to nitrogen is going to be very high if you increase the catalytic surface area. The reaction equation, that is, the decomposition happens when you break ammonia, you will get the hydrogen and nitrogen, 3 moles of hydrogen and 1 mole of nitrogen. So in order to break it, you need energy. So how much energy you need to provide to convert ammonia into hydrogen is, it is nothing but an endothermic process. You need to provide 92.4 kilojoule of energy per mole of ammonia to break ammonia into hydrogen and nitrogen. Okay. So that is for forward reaction. So for the forward reaction, you are going to produce hydrogen and nitrogen. Then if you want to convert again nitrogen and hydrogen to ammonia, it is called reverse reaction. There also you need, I can say, some amount of energy to recombine it. So enthalpy, for the enthalpy of formation, we can say here enthalpy change is approximately 92.4. So you need to provide this much amount of energy to break the amount. The decomposition reaction increase the number of moles from 2 moles. Here we are using 2 moles. 2 moles of ammonia converted to 3 moles. Okay, so that is a very important thing. So here, when you go for decomposition, the number of moles increase from 2 to 3 for hydrogen and 1 mole reduced. And because nitrogen is a reduction reaction, so nitrogen mole is reduced from, I can say, 2 to 1, which increases the disorder. So entropy is going to be increases. This change favors reaction, especially at elevated temperature. Because we are using high temperature, naturally entropy change is going to be higher. So irreversible process. The reaction pathway and rate control pertains to the ammonia decomposition. So what is happening in the catalyst? The absorption of ammonia on the catalyst surface. Assume that this is the catalyst surface. The green color shows this is the nitrogen. Then the blue color is nothing but hydrogen, three molecules of, I can say, hydrogen. Then you need to provide some amount of energy on the, maybe I can say, to break the ammonia. Here the decomposition happens at different states. Finally, the nitrogen separates, hydrogen also separates. At the exit of the reactor, you can take out the nitrogen and hydrogen separately. So breaking of hydrogen from ammonia is very easy, but it's for breaking of nitrogen from the ammonia is very difficult because there are 3 bonds. So it needs more energy for breaking the nitrogen into, I can say, atomic scale. So during dissociation, there are different intermediate species happening, NH, NH2, and different N2H. Different intermediate species going to happen. Ultimately, the purpose of the decomposition is to recombine the, I can say, hydrogen to form H2, then take out the nitrogen from the ammonia molecule. So the slowest step in this sequence controls the overall reaction rate. Catalysts like ruthenium and lichen helps to consume the minimum energy for the dissociation of ammonia. So equilibrium constant is an important parameter for catalytic reaction. For ammonia decomposition, the equilibrium constant increases with the temperature, meaning that higher temperature favors the formation of hydrogen ion reaction. So for any reaction, so you are finding out the equilibrium constant. So whenever the temperature increases, the equilibrium constant value also increases. So that is suggested by Lee-Chatelet, equation of the Lee-Chatelet principle. And they are saying that when the reaction rates are increasing, the conversion rate also going to be increases. That is the thing there. So here you can see here the endothermic process. How much the energy you need to break the ammonia by using catalyst is about 100 kilojoules per mole. Suppose we are not using catalyst, only you are providing only heat with sufficient temperature, then the amount of heat you need is 200 kilojoules. That is 2 times, alright, without catalyst, half a time with catalyst. So in order to form the nitrogen, I can say the amount of energy needed is only 50% of this. 50% of the, I can say, energy you supply to break the ammonia. So endothermic energy requirements, the endothermic reaction means an external energy supply is needed to sustain the decomposition of the reaction. Typically, the temperature of decomposition is above 500 degrees centigrade, depending on the catalyst. So if you are not using the catalyst, it may go up to more than 800 degrees, 700 to 800 degrees. By using the catalyst, then the temperature needed for breaking down is going to come down. So select the right catalyst so that at the minimum temperature, the endothermic process is going to be happening. The breakdown of the ammonia needs to be happening. So they tried with ruthenium, nickel, and all. So among the different catalysts, you find out which catalyst is going to consume minimum energy per mole of ammonia to break down to hydrogen nitrogen. That plays a major role. So catalyst selection is very important. So catalyst provides an alternative reaction path, as I already said. So it is not going to go for a conventional route. We go for a catalyst. Find out depends on the different catalysts. We find out the minimum energy to succeed our reaction. Okay. Catalyst provide an alternative reaction pathway to lower activation energy, allowing ammonia molecules to decompose more rapidly, more readily at lower temperatures. So surface size for reaction, you need to provide the catalytic surface area, more surface area, so that then the absorption of ammonia is going to happen and the desorption of hydrogen from the ammonia molecule also happen. That depends on higher surface area. Catalysts offer active surface sites where ammonia molecules can absorb, dissociate, and subsequently dissolve as product gases. This enables the reaction to proceed. So here you are going to absorb the ammonia, you are going to dissociate the hydrogen from the ammonia. The leftover in the ammonia absorption is only nitrogen. So we need some kind of energy to dissolve. So nitrogen will be, it comes out when you go for dissolving process. So they are using different types of catalysts. Is few we have listed: nickel, ruthenium, ion to minimize the activation energy at minimum temperature. You can able to do the dissociation process. They go for nickel due to its affordability and reasonable catalytic activity for ammonia decomposition. Nickel requires about 600 degrees centigrade for absorption, decomposition, recombination, as well as the desorption. So you need 600 degrees centigrade. Whereas ruthenium, you can see here, you need minimum temperature. Compared to this, when you go for ruthenium, the temperature needed in the reactor is 400 degrees for absorption, decomposition, recombination, and then desorption. When you go for iron, it's not as efficient as ruthenium. Iron is only used in, I can say, producing ammonia in the upper post. But when you use the same catalyst for desorption, it requires higher temperature. So among the three catalysts we are suggesting is you go for ruthenium to go for a conversion of ammonia to nitrogen is going to be happen at minimum temperature. Still you explore different catalysts and find out maybe at 350 degree or 300 degree or 200 degree or 250 degree. The process needs to happen. So you can able to minimize the energy input. You are going to the form of heat. You are going to given from the different source. So here you need a lot of research. So right. So one same I can say reactor. One catalyst has a need of 600 degree. Another is need of 400 degree. Then another catalyst is used for producing ammonia during upper post. It's more than the nickel. So need to see that. So we need to explore the different catalysts and find out because it is an energy intensive process. The way in which we can able to reduce the energy input is also reduce the cost of ammonia. I can say hydrogen generation from ammonia. So specific sites on the catalyst, metal atoms on the surface, facilitate the, I can say, breakdown of the bonds in ammonia, initiating the decomposition process. Catalyst must have an optimal binding energy for absorbed species. The binding is too strong, product won't dissolve easily. So we need to have absorbing and also the catalyst has the capability to dissolve the nitrogen after this process is going to be completed. So product won't dissolve easily, blocking the active sites. That's why you need to regenerate it. Whatever you are absorbing ammonia on the catalyst, you need to convert, decompose it to hydrogen. So the remaining leftover from the ammonia is only nitrogen, but you need some kind of energy to dissolve nitrogen. Then only the process, the number of active sites going to be regenerated and comes to the, I can say, next cycle. If the desorption is not going to happen, then the absorption is not going to happen for the next cycle. So need to ensure that how much is absorbed going to be dissolved. The absorption is ammonia, desorption is nitrogen. Okay, the ideal catalysts are ruthenium strikes a balanced electric efficient absorption, dissociation, and desorption. So from the previous slide, we found that so ruthenium having I can say at a minimum temperature you are doing it, able to do the I can say absorption, decomposition, recombination, and desorption is going to be better than the platinum as well as the ferrous. Reaction intermediate, there are different intermediates going to be formed, but at the end you need to ensure that it is going to come in the form of hydrogen, not in the form of NH or NH2 or N2 or something. So accordingly, the reactor needs to be operated, the catalyst performance needs to be enhanced. So need to give ammonia at the exit of the reactor, you need only nitrogen. If any intermediate comes out, then this is not going to be, we are not going to be attain our expectation. So compared with the thermal based, right? Assume that by burning the coal or oil, you are going to enter into the heat of 600 or 400 degree. And maybe you can use the heat by using a microwave also. Maybe this concept will be maybe tomorrow we are going to explain this one. Microwave, how the microwave and energy can be used for pyrolysis to break down the different biomass and the mixing of biomass with the plastics. How the microwave energy is going to be consumed, the minimum energy to get the maximum. So we are going to try with electrical pyrolysis. We are going to find out how much energy we are going to supply to get the desired output. Then you are going to try the same quantity in the microwave to attain the same better than that or equal to that. How much energy is going to be consumed for microwave? Also, if possible, we can try it in the plasma method. We can combine all three. We can ensure that why the microwave is going to consume minimum energy to get the maximum yield. So that depends on, because for all the thermal mode or the electrical heating mode, you are providing heat from the surrounding. Right? Some solar radiation reaching your body, right? Through radiation, convection, and conduction. Whereas the microwave, heat is generated inside the body. So the component called magnetron is there. So we are going to provide 20 kilowatts of frequency maintaining. We're going to create a microwave. Microwave is not created from outside, it's not not like solar radiation, goes inside. It's going to be created inside. Only thing you need to ensure that the microwave absorbing material needs to be there inside. Not to prepare rice or meat or fish, whatever in the microwave oven may come across. Hydrogen, the polar in nature is going to have the capability to absorb the microwave. Suppose you are putting some kind of dry product inside, the microwave cannot absorb it. So here, the microwave, the concept we can also bring here for producing ammonia from producing hydrogen from ammonia. And also we are going to, there's so much work done in the plasma technology also. The plasma assisted ammonia decomposition is an innovative approach that uses plasma to initiate the decomposition of ammonia into hydrogen and nitrogen. Okay. Saran, you can also try this. Maybe we can find out some system just sending water for electrolysis in the reactor. You can send nitrogen back and cut the water supply. Whether you are going to get hydrogen out of the ammonia, same reactor we can try. Plasma is an ionized gas. We all know that we are going to create a high intensity spot, right? So, in order to create a ionized gas, we create a plasma. Plasma is the fourth step of matter. The temperature is more than, I can say, people are claiming that more than 10,000 Kelvin. People are saying that is a plasma. So, the ionized gas, you can send air or nitrogen or argon or helium. So, through the high intensity spot, then the inert gases may be passed on to that. It is going to produce the ionized gas that's called plasma. That energy is going to be used for breaking down the ammonia into nitrogen and hydrogen. But we didn't have done any experiment on that. But people are using plasma along with the catalyst also. We need to think about, okay, we are producing ammonia, okay, we are going to try with a different, I can say, non-catalytic way and catalytic way. At the same time, people will ask, right, whenever I need hydrogen, how will you take it? Whether the same technology or same reactor can able to produce the hydrogen, we need to really work on it. Okay. So plasma generation, you already know that, generated by applying high voltage electric field to a gas with ionized gas molecules, creating a mix of electrons, ions and excited radicals. In ammonia decomposition, plasma is typically generated by methods like dielectric barrier discharge. There are different ways of creating plasma. You can refer some review paper. There are many ways they are using creating a plasma, high intensity, I can say, energy. So one of the thing is dielectric barrier discharge, what we are currently using in our laboratory. Similarly, microwave also used for creating a plasma or radio frequency plasma. Okay. So we will try for that microwave way of assessing plasma or a radio frequency plasma. Maybe in the future research, maybe we can think about that. Because the amount of energy consumed for producing, I can say, plasma through dielectric barrier discharge is very high. So if you bring the microwave energy for producing ammonia or radio frequency energy to produce ammonia to get the desired conversion, we need to explore it. So the reaction mechanism, high energy electrons within the plasma collide with the ammonia molecules, providing enough energy to break NH bonds and generate reactive species such as NH2, NH, atomic hydrogen and atomic nitrogen. So these reactive intermediates undergo further reactions, ultimately forming stable. So ultimately, whatever may be the energy you are going to consume, whether microwave or radio frequency or direct discharge through the plasma can be generated. So you can go for any intermediate reactions from inlet, but an outlet we need a stable product of hydrogen and nitrogen. Need to ensure that. So if the unreacted or the undecomposed nitrogen and hydrogen, again you will recycle it back and ensure that we will be getting only stable, the molecular hydrogen and molecular nitrogen. Some plasma reactors utilize surfaces, electrodes where additional reactions can occur, enhancing the decomposition efficiency. It's very simple. You can able to prepare a meal like rice or whatever, idli or whatever. You need only heat. They're going to give it from burning the wood earlier days. Then you are going to use the heat by burning LPG, right? Or from using induction, or by using a microwave, or by using a. So ultimately, to prepare, I can say to cook rice or to cook idli or prepare sambar, to prepare other, you need some amount of energy. Heat. Heat is placement. You can produce the heat in any way. But you find out that which one will going to consume minimum energy to attain that. For example, in our house, right, LPG is also parallelly running, induction also running, microwave also running. Because someone want to close the, I can say, cooking process as quick as possible, right? So among this, you can go through the different explanation. Among the different energy sources, microwave, radio frequency, induction, electrical, then thermal mode, you need to find out which is going to be cost effective for attaining the temperature. That you can take it for free. The electrochemical ammonia decomposition, similar to the fuel cell, right? The electrochemical ammonia decomposition is an emerging technology that offers a clean and efficient method of producing high purity hydrogen from ammonia. This process leverages the power of electrocatalysis to break down ammonia into its constituent elements, hydrogen and nitrogen, until binding conditions. Electrochemical ammonia decomposition involves the use of electrochemical cell, typically consists of anode, cathode, and electrolyte. Similar to fuels. If you are using hydrogen, you will get a water. Electricity will come out. If you are giving electricity, give ammonia into the same system, you are going to get hydrogen. That's it. Ammonia is introduced into the cell where it undergoes a series of electrochemical reactions. So simple, I can say, the schematic diagram of the electrochemical cell is the breaking of ammonia into hydrogen. You can see here. You are going to allow the ammonia into the anode side. So you have the electrolyte, you have the cathode. This is the negative terminal, this is the positive terminal. So ammonia is entered into the anode side, where is going to be ammonia is break down into, I can say, electron and the nitrogen. Hydrogen, because you know the electron will contain only the protons. So only hydrogen ion will move towards the cathode side, right? So there is going to, I can say, electron is going to be comes and combined with the hydrogen proton plus going to form the hydrogen. So here you can see here, so similar to the electrolysis process. Here the ammonia may be entered in the form of gaseous state or liquid state. It's entering into the anode side. Ammonia breakdowns into, I can say, positive ions or negative ions. Here positive ion is nothing but hydrogen. The negative ions are nothing but nitrogen and electron. Okay. So here electron and along with nitrogen is going to be comes out. Electron will be moves out from the circuit and is going to be recombined again with the positive ions come through electrolyte combined here with entering into the cathode. So positive ions leaving from the ammonia, the electron entering into the cathode from the anode is going to be combined here. H plus and electron minus will produce the energy. So ammonia molecules absorb onto the surface of the electron contains at the anode. The absorbed ammonia molecules undergo electrochemical oxidation, releasing electrons and protons. So the released protons migrate through the electrolyte to the cathode, where they combine with the electrons from the hydrogen gas. So nitrogen, the remaining nitrogen left over in the electrolyte part or near to the anode part, I can say, will be combined and going to come out from the reactor as nitrogen. So here you are going to take out the cathode side, you are going to take out the hydrogen as well as the hydrogen, and then the cathode you can take out the nitrogen. The exact reaction mechanism of electrochemical dissociation is can be very depending on the electrocatalyst and operating conditions. So these are the general mechanism. NH3 is absorbed on the surface of the anode, converted into NH2, then H plus electron. So H plus electron, H plus will move through the electrolyte to the cathode. Electron will move out from the anode. It's going to be combined with H plus available at the cathode. So H2 is going to be formed. Then NH2 already absorbed on the cathode is going to be again converted into NH, then again H plus. So there are three steps in which the ammonia can be dissociated. NH3 to NH2, NH2 to NH, NH to N. Okay. So the N is going to be there in the anode. It is going to be combined with another atom of nitrogen, forms nitrogen. Okay. So this is the reaction. NH3 to NH2, hydrogen comes out. NH2 to NH, hydrogen comes out into the cathode side. NH to N, then hydrogen comes out from the anode to the electrolyte to the cathode. So hydrogen will combine with the electron, produces H. Okay, H and H will combine again, produces H2. So the cathode side, ultimately you can say 2H plus 2 electron, we get H2. Advantages and challenges of non-quadratic and plasma system decomposition. Plasma system is advantages: low temperature, fast reaction, renewable friendly. Challenges: high energy need to spend for it, complex reactor setup. Okay, the electrochemical method of producing the desired reaction parameters. Electrochemical lower temperature advantages: high purity hydrogen can be extracted from electrochemical method from ammonia. Renewable electricity can be converted. But electrode degradation, because ammonia is corrosive nature, is going to degrade both cathode and anode. Slower reaction rate. When you compare with the plasma and I can say thermal mode, this electrochemical method is in terms of reaction very slow. Thermal decomposition is simple step. So you are going to provide the heat in the form of thermal mode by any source. You can use it. No catalyst issues. High energy demand. Thermal management complexities. So, what is it?
Process
Optimization. Okay, we need to focus on catalyst part, reactor part, then operating conditions. Okay. Catalyst development, you need to try ammonia, can say, along the catalyst. There are different methods are available for absorbing, I can say dissolving, decomposition and recombination. You can try with different catalysts and find out suitable catalyst which is going to produce the hydrogen and nitrogen with a minimum amount of energy. Okay. So the catalyst development, lot of research is needed. High activity and stability, developing catalyst with high activity and stability towards ammonia decomposition is crucial. So lot of research is necessary. And we need to think about not only for higher activity and stability, the cost also. Utilizing inexpensive and abundant materials can reduce the overall cost of the process. Then you can go for nanostructure, that means you can able to increase the surface area of the catalyst. So instead of buying a nanocatalyst from the market, you can able to buy it maybe in some micron size or mm size. There are some processes available to converting the catalyst to nano size. The nano synthesis process you can need to encounter. Then the reactor. So the reactor needs to be ensured that there will not be any much loss in energy, heat loss from the reactor. That's why we said microwave is going to be better than other type of process because heat is generated inside. The heat loss is going to be from inside to outside. So the system is highly insulated. So there is a heat loss going to be minimum. Whereas if you talk about the, I can say, plasma, if you maybe plasma also similar to microwave only. We talk about the electrical heating or the thermal mode of heating. It is coming from surrounding. Actually, know that it is goes from high temperature and low temperature. So the temperature around 1,500 to 2,000 degrees centigrade. Ambient temperature is maybe I can say 30 degrees. Instead of reaching that desired amount of temperature to the reactor due to the atmospheric temperature, So heat loss will be going to happen. How much is the conversion? How much the actual conversion if you go for empirical and thermal mode of heating? It's going to be the question. Okay, so efficient mass transfer optimize the reactor design to facilitate efficient mass transfer of reactants and products are essential. How much is entering? How much is leaving? So we need to ensure that suppose you are sending around one ton of ton per hour of ammonia into the reactor. We need to ensure that the combination of hydrogen supposed to have same value. Okay. So we are not interested in, I can say, intermediate species comes to the reactor maybe outlet of the reactor. So we need to balance the mass. And what is entering, what is leaving. Should be remain same. Mass entering into the system supposed to be mass leaving the system as per the law of conservation of mass. Okay. So effective heat management can improve the reaction kinetics and energy efficiency. What are the ways you can able to save the heat or reduce the heat loss from the system to the surrounding or surrounding to the system? The pressure, you need to ensure the pressure because higher pressure always leads to, I can say, poor reaction rate. Operating conditions, temperature, pressure, and feedstock purity needs to be ensured because if you want only 400 degrees for particular reaction to happen, based on the particular certain catalyst, we go above also you are wasting the heat. Okay. So and also if you provide lesser heat also, it's going to be not going to be converted completely ammonia into hydrogen and nitrogen. So need to exactly find out the operating window, it means what is the temperature, what is the pressure, what is the purity of nitrogen I need to provide into the reactor so that I will get the 99.9% efficiency conversion happen in the reactor, and also the purity of hydrogen supposed to be, if you want to use it in a fuel cell, it should be 99.9%. So that purity needs to be ensured by properly selecting the catalyst reactor as well as the optimizing the operating conditions. So ammonia combustion. So ammonia combustion, we are saying that is going to be useful for an engine, internal combustion engine. If you want to completely eliminate petrol or diesel or gas, fuel, LPG or CNG, completely to eliminate the carbon dioxide emissions, the only option is replace the I can say the conventional liquid or gaseous fuel into ammonia. But ammonia is having a calorific value, a decent calorific value of about, I can say, 50% of the calorific value of the diesel or petrol, maybe around 40%. But we need to increase the size of the fuel tank. But the only product comes out apart from the water, I can say, oxides of nitrogen. You can use the SCR kind of technology, scientific reduction technology. You can break down the NOx to the acceptable level. As per Bharat 6 norms or I can say European norms, need to ensure that the norms are maintained, the NOx is in a controlled level. Ammonia combustion, ammonia decomposition are closely related but distinct processes. Ammonia here, ammonia decomposition is it doesn't require any oxygen, you need only heat. You provide the heat, ammonia converted into nitrogen and nitrogen. Suppose we are providing oxygen, so it's a combustible gas, it's going to react with the oxygen, produces nitrogen and water. Ammonia and oxygen reactants, products are nitrogen and water. Suppose if it is the temperature of the reactor is less than 700 degrees, there is a point where the NOx formation happens in the engine. We are able to control the temperature. You have only two products, only nitrogen and water, not water vapor, I can say. Suppose the temperature of the reactor, maybe the product maybe reaches during combustion is more than 700 degrees, you cannot avoid the oxidation of it. Okay. So this is an exothermic process related approximately 160 kilojoule per mole of heat. Okay. So when you want to break it, it is consuming around 200 kilojoule per mole. Now to break the ammonia into nitrogen and hydrogen, for thermal mode you are providing 200 kilojoule, but when you are burning the ammonia, it liberates this much amount of heat per mole of ammonia. Ammonia combustion can help in ammonia decomposition indirectly under specific conditions, especially in scenarios where incomplete combustion or controlled oxidation process occurs. So comparison of ammonia combustion and ammonia decomposition, you can say, is a oxidation process. This is a thermal decomposition process. Ammonia decomposition. So reaction of ammonia with oxygen produce nitrogen and water. Here breakdown of ammonia into hydrogen without oxygen. So we need only something only heat. That's called endothermic process. When you apply only heat, your ammonia break down into nitrogen and hydrogen. Suppose you want to burn it, then if you are providing oxygen, assume that even the thermal decomposition reactor, you need to ensure that the air presence is going to be zero. Right? You need to provide some amount of inert gas, you need to circulate it, to ensure that the purging of air happens in the reactor. Okay, if the oxygen is there, naturally going to lead to the exothermic process rather than the endothermic process, produces water vapor and so it produces during the exothermic process when ammonia burns, produces heat value of 1160 kilojoules per mole. Now to break down ammonia into nitrogen, you are providing energy input of 92.4 kilojoule per mole of ammonia. So right, requires oxygen as a reactant, no oxygen is involved. Products, nitrogen gas and water, and also possibility if its temperature is more, naturally oxides of nitrogen also will come. Nitrogen gas, water, and oxides of nitrogen. NOx. Here the products only nitrogen and nitrogen. Because the temperature here is near to I can say 700 degrees centigrade, 400 to 700 degrees centigrade. There is no oxygen available for this process. So there is no possibility of oxygen supplement for thermal decomposition. The energy source can serve as a fuel, producing thermal energy or powering engines. Used as a method to produce hydrogen for energy storage for fuel cells. Okay. So reaction conditions can occur spontaneously at elevated temperatures or with a flame enhanced by catalyst. Okay. So it produces high temperature. So the claim what we are claiming products only nitrogen and not water is not so. Oxides of nitrogen is not going to be available. Here the reaction conditions require high temperature, 600 to 900 degrees centigrade, or catalyst like lithium and nickel and ferrous can be brought in to bring down the temperature slightly lower than. So applications for ammonia combustion, we are using ammonia as a fuel. If you go for oxidation mode, then what are the applications? You can use for gas turbine as a fuel for producing the power. Even the aviation sector, ammonia can be considered as a fuel for I can say for carrying the passengers or carrying the goods, particularly for aircraft applications. But you need to ensure that the components of gas turbine and other components exposed to ammonia is free from combustion. So wherever suppose you want to only heat, then the places like Antarctica or places like where you need to heat the room, you can use ammonia as a fuel for heating the room also. Okay. Then ammonia based combustion engines or internal combustion also you can use as a fuel. Then application here is ammonia decomposition is hydrogen is coming out, naturally it's going to be fuel cell. Hydrogen production for fuel cell, chemical synthesis and storage for renewable. So whatever maybe the nitrogen comes on, or nitrogen comes on, you can take out both the things, and hydrogen you can use it for fuel cell, nitrogen you can use it for some other synthesis process. Challenges and future directions. While ammonia decomposition offers significant potential, several challenges needs to be addressed. Catalyst deactivation, energy efficiency, scale up. Developing catalysts that are resistant to deactivation due to coking and sintering is crucial. Energy efficiency, improving the energy efficiency of the process, particularly for heat source is essential. So what is the type of heat source you are going to provide? So that the minimum energy can be given to attain the required temperature. Either by using a radio frequency or microwave or plasma or electrical or intensive type of energy mode to produce the heat. Scaling up the process because whatever the research what we are doing, it is in the laboratory scale, that is the DRL5 level. Suppose you want to scale up from I can say 100 kg to a few thousand tons, then you need to ensure that whether it's going to multiply the required quantity is going to attain the performance. Scaling up the process to industrial levels while maintaining the high performance and efficiency is the major challenge. You cannot just multiply it. So 1 ton for our reactor geometry, we go for I can say multiply by 10 times, then you can multiply everything by 10 times, not possible. Okay. So future research efforts should focus on developing more efficient catalysts, optimizing reactor design, and integrating ammonia decomposition with other energy systems to create more sustainable and cost-effective for hydrogen. So this is very important. So whether you are going to use the energy for decomposition of ammonia, if you take it from renewable energy sources, then the amount of energy you are spending for breaking up the ammonia into hydrogen is going to be cost-effective way of producing hydrogen. The different case study, I can say Linde is the leading company dealing with, I can say, ammonia. So that is the person, actually, I can say, the invented the refrigerant, you can say ammonia. These are the group largely working on low temperature applications, Linde. Here they are Linde technology traditional method. They are coming with ammonia as a feed material. You can see here. Linde technology, they have come up with a system 1000 to 5000 normal meter cube per hour. If you load it, the traditional method 1000 to 3000. Hydrogen here they are claiming 27 kg of hydrogen per ton of ammonia. They are able to get it from Linde technology. The traditional method they are producing about 25 kg hydrogen per ton of ammonia. So ammonia conversion efficiency here 90 to 95%. Linde is claiming. The traditional method, what I think we have discussed, is comes around 88%. Operating temperature, the traditional method is 850 degree, but Linde method is comparatively 150 degree lower than that. Energy consumption is going to be compared to the traditional method. It's about 1000 to 1500 unit of electricity you are going to provide, or thermal energy you are going to provide per ton of ammonia. Then here for conversion to the traditional method, we are providing 1500 to 2000 kilowatt hour per ton of ammonia. The conversion efficiency is hydrogen purity here. They are claiming 99.9% from using Linde technology. Then here our traditional method also they are able to attain the same level 99.9%. The Linde group is a global leader in the production of industrial gases. Implemented ammonia decomposition technology as part of the strategy to produce high-purity hydrogen. Hydrogen is in demand across various industries, including energy, chemicals, and semiconductor manufacturing. Ammonia often produced from natural gas or through a electrolysis process is a convenient hydrogen carrier. Decomposing ammonia into hydrogen and hydrogen is an essential process to meet the growing need for clean hydrogen. Okay. Summary: ammonia decomposition is a promising technology for producing clean and renewable hydrogen. It involves breaking down ammonia into constituent elements hydrogen and hydrogen. This process is typically catalyzed to enhance the reaction rate. The decomposition reaction is endothermic, recovering heat input. The produced hydrogen can be utilized in various applications, including fuel cell vehicles and industrial process or internal combustion engine. However, challenges such as catalyst deactivation and energy efficiency needs to be addressed to realize the full potential of this technology. Conclusion: ammonia decomposition presents a promising avenue for producing clean and renewable hydrogen. By developing highly active and stable catalysts, optimizing reaction conditions, and improving energy efficiency, this technology can contribute to a sustainable energy future. Addressing challenges like catalyst deactivation and scaling up the process to industrial levels are crucial for commercial viability. Further research and development efforts are necessary to fully unlock the potential of ammonia decomposition as a clean hydrogen energy source. So these are the references we have used for preparing the PowerPoint. Do you have any questions? You are most welcome. In this there are so the last lecture we are focusing on producing ammonia from hydrogen, different methodology we are. Now you are having hydrogen ammonia, whether you are going to use the ammonia directly as a fuel, or you are to use the ammonia as a, I can say, you want to decompose it, use hydrogen as a fuel cell. So the conclusion from this presentation is you can use it for any application. Ammonia can be used as a fuel in gas turbine, that's directly, and engine directly, but you need some kind of challenges to in terms of the material compatibility of the gas turbine components as well as the internal combustion engine components. Right? We are also really want to know how the ammonia can be used in our internal combustion engine. We need to really go for tribological study friction, wear, and tribological and the lubricating oil behavior when the ammonia is encountered as a fuel in the internal combustion engine. We need to try with diesel for as per the standard, IS standard. We need to run for 500 hours. Take out all the components exposed to the diesel or combustion products. So we can put a tribological study for all the components, start from aluminum, cast iron, copper, everything. We need to go for it. We tried with biodiesel actually. We tried with biodiesel. We run it with 5 hours per diesel. Then the same number of hours we tried with biodiesel, and we proved that the biodiesel is going to be, I can say, no need of any replacement of the material, they go for biodiesel. But some component needs to be, I can say, coated against the corrosion, particularly prone to corrode with rubber as well as the copper components. So we are using water many places to avoid the leakage, right? So wherever the copper components are exposed, similarly for even for the fuel injector, fuel pump, there are some elements are associated with the copper. So you need to, the copper is close to oxidation, but the biodiesel contains oxygen. Here, I don't think there is no problem for oxidation, particularly because contain only nitrogen and hydrogen, but this is corrosive nature. The property itself is corrosive. So we need to ensure that at the point of, I can say, storing the fuel in the tank, through the fuel tank to the pump, and then from the pump to the engine components, all the components should be exposed to the corrosive environment. So what people are doing in particularly, they are doing in to construct a Bombay bridge, right? The new Bombay bridge, they are going to launch it probably in a couple of days. There, all the materials are exposed to the saline water, prone to corrosion, right? So what the type of the coating they are using, what material they are going to use it as a material to avoid the corrosion in the exposed to the different oxidation environment, different temperature, different salinity level, they are exposed to high pressure, maybe the pressure, wind blows, right? So all the conditions they are exposed to the different cities are done. Maybe same thing can be done for our high temperature corrosion here. Whereas there is low temperature corrosion, for Bombay bridge and here, you need to do some kind of study for high temperature corrosion. So we have a corrosion center of NADC, we can able to do it both low temperature and high temperature. Because from the fuel tank to the pump and also low temperature. When it's fuel injected into the component, the fuel injector, then the piston rings, piston, right? Then the cylinder liner, crankshaft, camshaft, all the components are, even the valves are exposed to high temperature. So we need to do the high temperature corrosion also to study the behavior of the fuel, how the ammonia is behaving at high temperature. So we'll break for tea. I think you can come back around 11:30 for the next session. Professor, who will join? I think my lecture is over.
Morning session upload.